Okay, this is Giancoli Physics AP edition, 7th edition. We're working in chapter 10, fluids, and we're currently working on problem number 24, so let's dive into that one. Problem 24 reads, a geologist finds that a moon rock whose mass is 9.28 kilograms has an apparent mass of 6.18 kilograms when submerged in water. What is the density of the rock? Go ahead and pause the video, wrap your brain around this problem, and see if you can come up with a plan. Okay, so our problem solving strategies, we identify the numbers we're given. Let's go with green today. And we have a mass here, which is the mass of our rock. We use m sub r for that one. We have another mass over here, which technically is still associated with the rock, but it's the apparent mass after submerging in water. We'll call it m sub a for the apparent mass. What they're asking us for here is the density of the rock. We use sub r again. I anticipate we'll need some other densities here, so we're using subscripts. Now, for a little bit of background here, when they're talking about apparent mass when submerged in the water, what they're talking about is, let's just imagine you have a beaker over here. I need some room for a spring scale. I have a spring scale over here with measurements. We'll talk about that more in a second. And I suspend my rock from my scale, and I submerge that in the water. What this is saying is that spring scale reads 9.28 kilograms out of the water and 6.18 kilograms in the water. This is due to, as you may be aware, when the rock gets submerged in the water, it displaces the water out of the way, and the weight of that water pushes back and provides a buoyancy force on the rock. So that's what's accounting for the difference. Now, just a side note, these scales read in kilograms. They're really measuring force, but even if you have a scale at home that's measuring in SI units, it will likely read out in kilograms, which isn't technically a force. It's not a force of gravity. It's not really your weight. It's actually your mass. But it is measuring force or weight, and it's just calibrated to read in the associated mass. So that does create some unit confusion with some folks. Anyway, moving on. At the end of the day, they're asking us about the density of the rock here. By definition, the density is going to be the mass of the rock, which is a number we already have. We know the mass, divided by the volume of the rock. The trick here is we don't know what the volume of the rock is. And there's an old story about determining whether a crown is made of real gold or not by using this same principle, by submerging the crown in the water and seeing how much it displaces. So I don't know the volume of the rock, but what I do know is the difference in the mass here between the actual mass and the apparent mass. And the difference is due to the mass of the water that has been pushed out of the way. So because of that, I know the mass of the water pushed out of the way. It's the difference between these two. And since I know the density of water, I can then also use that to calculate what this volume is, because the volume of the rock is going to be the volume of the rock displaced, or the water displaced. So I can replace that volume of the rock with the volume of the water, and then likewise replace the volume of the water with the density. Correction. Density is defined as mass per unit volume. So the volume of the rock is going to be, the volume of the water is going to be the mass of the water divided by the density of the water. And as previously stated, I'm going to go ahead and move that density of the water to the numerator since it's in the denominator right now. The denominator of the denominator. That frees up a little more space down here for the mass of the water, which, as we said before, was going to be the mass of the rock minus the apparent mass, because it's that difference that it's the mass of the water that's accounting for that difference, providing that buoyancy force. This gives us the density of the rock in terms of the mass of the rock, density of the water, which I know, and the mass of the apparent mass that I also know. Now we're ready for some numbers. We'll need the density of water. You can grab it from table 10.1 if you want. However, density of water is a fairly commonly known. If you've been working with these problems for a while, you're probably familiar with it and don't need to look it up. But the mass of the rock is 9.28 kilograms. Density of water, 1 times 10 to the third kilograms per cubic meter. Then we're going to divide that by 9.28 kilograms minus 6.18 kilograms. Again, that difference indicating the mass of the water that has been pushed out of the way or displaced. This difference down here is going to give us a value of about 3. 9 divided by 3 is roughly 3. So this should give us roughly 3 times 10 to the third kilograms per cubic meter for the density of the rock. We expect about 3,000 kilograms per cubic meter for this rock. It's very dense moon rock. So go ahead and grab your calculators and let's see what you come up with. And my calculator is telling me approximately 2.9935. And that is times 10 to the third kilograms per cubic meter, which is very close to what our mental math was telling us, so we can have confidence in that. We're working with 3 significant figures in our problem here. We'll go ahead and more appropriately around this to 2.99 times 10 to the third kilograms per cubic meter. You could list that as 2,990 if you wanted. But the density of our mystery moon rock is approximately 3,000 kilograms per cubic meter. That does it for this problem. We'll move on to the next.